about to buy this house in Sunset Heights, and I'm pumped to be back.
Oh, okay. That's great.
I don't remember August being so hot. I was here all of August, and then in the past, El Paso summers were pretty nice. Particularly in August, they would be kind of cooler. It was scorching. So I guess global warming's caught up with us.
Yeah.
Right.
Yeah.
Right.
We usually get a lot of rain in August, and we didn't see any this
All
year.
right. That's why, right? And the rain really cools everything off.
Yeah. With the dry heat, it's so nice.
So. Right. Well, it's getting nice now, though, for sure.
Yes.
All right.
Okay,
You want me to go ahead? Go?
Yes, I think we have enough attendance. Students are still joining in, so I think that's good. We can get started.
Okay. So in any case, I got to tell you, I was here from 2003 to 2016, and I was in the electrical engineering department. And I had an opportunity to come back to UTEP, and of course, mechanical engineering, I think, is the flagship department. So of course, when I got an invitation here, I took it. I can tell you that I've been under a lot of pressure. These are my 6 kids, and I have 5 daughters and a son, and they've all been just hounding me to come back to El Paso. And so much so that my son, who was just graduated from West Point, the Army Institute, near New York City, he actually asked to come back to El Paso instead of going to like Germany or Italy, which I thought was kind of funny. And in any case, I'm living in a room with a couple graduate students. I won't say their names because it'll embarrass them. But I just went under contract for this house that's in Sunset Heights. And I was just telling everybody that was on the phone prior that I'm really excited to be there. It's going to be a cool house. We're definitely going to have department barbecues at this place once I move in. And I would tell you that in the period that I was here, 2003 to 2016, we did a lot of really interesting research at UTEP. These pictures on the bottom left show 3D printed electronics. And I worked with David Espeline, Frank Medina, and Ryan Wicker in the Keck Center. And I'm really coming back for those professors, those researchers. But I'm not really going to talk about that today. If you're interested in it, right as I left, we had a review article in the journal Science, and it gives a really good, overview of all the work done at UTEP and at other schools as well. But UTEP dominated during the 2003 to 2016 timeframe. And so if you need that article, let me know and I can get it to you. And then just a shameless plug. I can hear somebody on the keyboard. Is that possible to mute? I don't know who it is, though.
Yes, we'll mute them.
Okay, good. All right. So in any case, I'm missing something. I want to do a shameless plug. Right before I left, Ryan Wicker and I co-founded a journal on additive manufacturing in the Dutch publishing company Elsevier. And it is currently the #1 journal, impact factor-wise, for all manufacturing journals worldwide. It's kind of just dumb luck. We started a 3D printing journal right when 3D printing really took off in terms of pop culture. And we have done a pretty good job of keeping the time to first decision, under 2 months, and while maintaining a real high level of scholarship. And so just the quality of the articles that go into this journal tend to be the best in the world. We get papers from all over the world. And I think it's, the best of the 3D printing journals. And I think technically it's the best of any manufacturing journal currently. And if you guys are interested, we want more UTEP papers for sure. But if you want to just ask me about, if something's within scope or if it's got the quality level required, I'm definitely here to help. So, publishing, I think, is the foundation of graduate school and getting a master's or a PhD. And it really provides the credibility if you have these publications that are peer reviewed in high impact journals. So really want to take advantage of the fact that this is housed at UTEP. So I was telling you that I'm not going to talk about what I did at UTEP, which was 3D printed electronics, but I have had about 10 or 50% of my research in the last 4 years while I've been in Ohio. I went to Youngstown State, which is the backyard university for the America Makes Institute, which is a federal institute for 3D printing. I kind of went there to get closer to the mothership. UTEP is a satellite university of that institute. But I went there and just got access to different things and got to learn new things. And some part of my research remains 3D printed electronics, or at least when I was there. And specifically, if you see this shoe, that photopolymerization has come a long way. There's new processes which are faster. The materials are incredible. They're durable enough that they can print shoes, which you're going to step on 100,000 times. And it's just a testament to the durability. But what they do essentially is in one way or another use light to set the shape. And then they have some sort of thermal UV cure after the fact to sort of imbue the mechanical performance, the mechanical properties that are much better. And so what I've been trying to do is something called overmolding, where I could take two pieces that have a complex, mating surface, and I can, like a 3D jigsaw, I can put these together after they've been printed, put them in the UV curing oven, and they consolidate. And the idea then is all those superficial surfaces can be populated with electronics. You could assemble it and then overmold it and cure it together. And you can have 3D printed electronics where you have the wiring, sensors, microprocessors, just in any arbitrary location in any orientation inside of a complex structure. And so the shoe is what really got me excited. I got invited by the CEO of Carbon 3D that does the Adidas shoe. Unfortunately, I never really got very far with that team. They're a startup and they're really busy. But I did get something better that I'm about to show you in a moment. So here you see the sphere to the side. You can see how it's 4 pieces, and you can see that there's electronics inside of it, and then it comes together, and it might have a mortise and tenon system to increase the surface area and help in the mechanical connection. But once you print those 4 pieces, assemble them, put them in a UV oven, it becomes a solid sphere with embedded electronics. And here's a little tensile bar with a couple wires sticking out of it, just an early example. And so this is a video. Now, this is not carbon. This is Formlabs, and it's a material called New Balance, which is Rebound, which is going into the New Balance shoe. And it's not available, but I talked the company into printing this lattice structure for me, which was the work of a PhD student. And you see there's 2 wires going into it. And I don't hit very hard. That's a little embarrassing. But the idea that we're making a complex capacitive sensor that can measure deformation. And if you see my computer in the background, you can see that we're actually live streaming that. And that whole little red board can be consolidated down to just a small chip that can be hidden in the lattice, which is sort of the next step. And we're working on that. I published a paper if you're interested. Anything in green text is a paper that's been published or will be. And so if you're interested, you can explore it a little bit more. And all of this was sort of, was really inspired by the fact that the NFL, the American National Football League, had a symposium in Youngstown because of America Makes, talking about this helmet challenge. So they wanted to get 3D printed helmets that could help to reduce concussions by really tailoring the mechanical performance of the padding inside the helmet with spatially varying lattices and so forth. Okay, so this is kind of interesting. I just want to point this out because there's a lot of grad students in here. Publishing papers in journal articles is the foundation of everything I do. Every project I work on, it's moving toward a journal article. And then that journal article can turn into a proposal or so forth. But one thing that's interesting in today's age is that social media has become more important. And that video I just showed you, I put on LinkedIn, and it got 100,000 views. And it's fascinating to see who was watching it. Airbus, almost 300 people at Apple saw that video. Boeing, Intel. Siemens is a part of my team that I worked on with the NFL, so that's not surprising that they had a lot of people. But you could just see that it's all over the world. India, France, New York, Boston, the Bay Area. And so it's just something to think about that, as a researcher, I'm really kind of a used car salesman. I'm like out selling my stuff, right? Saying, look, I've got the solution, give me some funding and let me pay my grad students to go and explore it for you. And this is, I think, a powerful new avenue. I think you still have to publish those stodgy journal articles, but I think at the same time, 10 or 20-second videos that quickly get to the point and sort of show a compelling story are very important today in today's age of Facebook and Twitter. So just a couple more cool videos. This was a paper we just submitted, but we're trying different types of materials and different lattice structures. Siemens, a group at Princeton, New Jersey, in their advanced research group, has a geometry generation software group. They generated the lattice here, which is spatially varying. And then we took 2 materials, one that was compliant and one that was more stiff. And we are looking at high-speed imaging here of of absorbing energy. And we made it to the very final stage in the NFL challenge. There was $1 million up front that you could get, up to $1 million or share. But we didn't have a helmet manufacturer on our team, so we didn't make the final cut. But those that did are now in a 1-year contest that next summer they will hit a helmet at 6 different locations at 3 different speeds, and they have some sort of test that they have that they can get a metric. And if you can beat a metric, there's $1 million. They do this every year. And so now that I'm at UTEP, I intend to do this again, hopefully next summer, going for the summer after that. And we're continuing these studies with Siemens. And there's also a research institute in Merida, Mexico, that is working on this with us. And then this is, I think, also interesting. This is another lattice. Now, this isn't an elastomer, which are the soft materials I just showed you for the shoes. This is PEEK, and it's one of the strongest thermoplastics available. And the one on the left is a sort of a low energy impact, and the one on the right is a high energy impact. And what's interesting here is that this material is so hot that there's never been a dissolvable, soluble support material, which is what you need if you're going to make a lattice like this that has this overhanging structure. So by using the support material, we're able to do this lattice, and you can get these really light, very, very strong pieces. The only problem is they're brittle. And actually the football helmet challenge specifically says that you have to have a helmet that would last 10 years, as opposed to, say, a motorcycle helmet where you would throw it away if you had an accident. This would be appropriate maybe for a motorcycle helmet, but not for a football helmet. And this paper should be coming out pretty quickly. We're doing testing right now, and we're working with a company in Poland and that does this material. We think we're the only ones so far. They are the only ones so far that have this soluble material. It's just a matter of time before it becomes commercial. But we're trying to publish a paper, early on. And then this is interesting. This is a South African university that's helped us. They're doing CT scans. The color coding here is CAD compliance, dimensional compliance. So green is good, pink, those pink zits are terrible. Well, they're not really a problem for the mechanical performance, but that same piece you just saw get squashed, you're gonna see where the compliance of this in terms of, CAD to actual. And this always makes me want to eat Skittles whenever I see this. I don't know, do you guys see the video? I guess I'm hoping you see it. We're flying through the lattice right now.
Yes, we can see it.
Okay. All right. Does it make you want to eat Skittles also, or no? Is that just weird?
I think nerds.
Gotcha.
They were interest for me.
Got it. But so in any case, very high performance plastic now can be made where you have these overhanging structures in complex lattices. And so the idea of energy absorption, very interesting stuff, but probably not the NFL. So, and then I told you that I'm not doing a whole lot of electronics, but I guess I'm continuing to show you more of them. This is something I did with Carnegie Mellon and Rutgers, where we did a microcontroller. We have a little carbon nanotube well here to make a sensor. This is one puck. We put the electronics in, connect them together with conductive inks, and then we have a top lid that goes over it. It's a dome-like feature. And notice it has microfluidic channels that go down to the sensor, which is sensing explosives, or a precursor for explosives. Pedro Cortez is a chemical engineer that I work with at Youngstown State, and he came up with the sensor. But the idea then is we're overmolding those two pieces together. That protects the electronics, but yet we still have access to the sensor with these 3D fluidic channels. And it's just really interesting. And my PhD student at Youngstown State, who's still there, is working on a variety of different sort of wearable applications of this. And we don't have any publications on this, but we'll soon. And then this is kind of a cool project. This was done a long time ago at UTEP. But I got another project at YSU where the CEO of this company, which is a Sandia spinoff, they do this aerosol jetting where they put down these ultra fine lines and can go right to a silicon chip that's unpackaged. This is basically a computer without the package. And each of those little dots on the side are like the connection points. So we can basically connect it, we can power it, we can program it. It's a full computer and it's about 2.5 millimeters on a side. And in this case, it's in a pill that you potentially could have a computer in a pill and it would be ingestible, which is, interesting. Unfortunately, this red material, I'm pretty sure is toxic. So you would never want to take this pill, but the idea just as a demonstration is kind of cool. And I don't have anything to show about this, but at Youngstown State, we just landed $7.5 million from the Air Force Research Labs. it's congressional funding from our congressman there, who actually works with Veronica Escobar closely, but it's not like this was merit money, like where I, went to the National Science Foundation, but it's still funding. And it's like trying to figure out ways to 3D print things in such a way that they have a unique signature that is impossible to replicate, so that somebody can't make a 3D printed electronic piece and say, oh, here it is, this is what you built. And you find out later it's got some sort of, latent defect intentionally introduced into it that could cause a plane to crash or something like that. In any case, I intend to continue working with Youngstown State, get some UTEP students involved in that. And there's some interesting things we can do. And then, okay, so now I want to switch gears a little bit and say that UTEP is known for ceramic printing, but Youngstown State also has some interesting stuff. We were the first city in the United States to get an Israeli printer called the XJET. And it material jets down a nano solution of ceramic particles. And then, so you get the resolution of ink jetting, but then you have to put it into a sintering, furnace to get, fully dense ceramic. And it's really interesting. This is not me. This is Draper Labs, a MIT spinoff, and it's inspired me to basically try to reproduce this. So here you see the sinusoidal disc, and in it, with aerosol jetting, you see a spiral of silver, which is an antenna. And what's cool about the zirconia ceramic, two things. One is it's low loss for electromagnetic radiation, so it lets radio waves get through. And it has a permittivity of 30, which is the highest permittivity printed near full density. And so permittivity, if you're not familiar with electromagnetics, basically is related to the speed of light. So if it has a permittivity of 30, electromagnetic energy slows down by 30 when it goes through this. Now, the reason why that's interesting here is it sort of makes the antenna look larger because the wavelengths are extended. And so you have this small antenna, but it looks like the size of a Volkswagen. And we worked with North Carolina State to do this paper where we really examined that. And that was a year ago. But this is why it's cool. This is a ceramic lattice. So ceramics are just hard to print, right? They have a really high melting point, so they're just not printable generally. And when you put them in a furnace, they want to shrink and they want to crack. And so it's really difficult. But this is a lattice with 1 millimeter unit cells. And what's cool about this, and maybe I could show it here, is I can spatially vary those. So over here, you can see that same lattice spacing is there, but it's much thicker. So the ratio of zirconia to air is much higher than over here, where it's more air and less zirconia. And it turns out that when you do that, the effective permittivity can be changed from one side to the other, which means you can change the speed of light from one side to the other. And there's just some fascinating applications of this, really, to do lenses. So there's a professor at the University of Arizona that had this thing called a Lumberg lens. It's a lattice and it's sphere shaped, but it's dense in the center and it gets progressively less dense as you go out. And so as light comes in broadside, not light, electromagnetic energy, light would be at a too small of a wavelength for this, but radio waves come in broadside and parallel, and they get focused to a point on the other side of the sphere. And so there's really interesting things going on there. We're working on a paper right now with Lincoln Labs, which is basically a research center at MIT, and Ohio State, and actually a university in South Africa that they're doing CT scans, and they're giving us the effective density of each cell. And so we're trying to do electromagnetic simulations with that. And so, yeah, okay, this is a really cool project. It hadn't even started. I got contacted last week by this company called Made in Space. They have a printer in the International Space Station, just a regular, material extrusion printer. And it's been there for a long time. David Roberson had a project where he worked on investigating recyclability of the thermoplastic inks, filament, so that an astronaut could do an experiment with the wrench that they printed and then scrap it, pull it into filament, and then print something else. Because when you're in the International Space Station, you obviously don't have access to new spools of polymer. And so recycling it's very important. But these guys are using vat photopolymerization now, which doesn't make sense because vat photopolymerization has a vat of liquid plastic. And in space, that I'm guessing it's just going to float off into globs, right? So they figured out how to do that, which is cool. But what they're really interested in is putting ceramics into them, and you can print them, and then you can fire them in a furnace in the International Space Station. And they think that the ceramics are going to get a big boost in performance because they're fabricated and sintered in a microgravity environment. And so they have a printer on Earth, and they have a printer that's going into the International Space Station, and they're asking me to collaborate with them. I just talked to them last week, so I'm not sure where this is going. I'm not even sure why they're coming to talk to me. I guess I've got a lot of publications on ceramics, but to be able to print something in space, I'm so pumped. I can't even tell you. I couldn't sleep the night I talked to them. And then, like I said, ceramics are a nightmare to print. And the reason why is because they crack. So I printed these little 1 centimeter cubes. I sent them off to my friend in South Africa, who I met because the second oldest 3D printing conference is RAPDAZA, and it's usually in like Johannesburg or Cape Town. I've been twice. I'm going to be actually a virtual keynote speaker there in November. But he's really good at this. Professor's really good at CT scans. So I sent a bunch of parts to him, and he goes, "Man, your parts are terrible. They got these cracks right in the middle." And it's like, oh no, that's terrible. And so we're trying to figure out how to sinter them, maybe more slowly, where we ramp up the temperatures more slowly to fix this problem. But there's something called hot isostatic pressing, where you can put these into basically a hot liquid oil, and it gets compressed at really high pressure, really high temperature. And they do this often for like titanium parts that go into airplanes to close off internal pores. Any pore or crack that goes to the outside, the oil would get into that and it wouldn't help it. But any internal crack, it can potentially fix. And so we're about to publish a paper where this is that same cube. This is 2 different slices before and 2 different CT slices after. And you can see that that crack is gone. But we just squeezed the poop out of it. And in the end, we got fully dense parts. Now, if you think about this also, that lattice I showed you, you could do that with that as well. And it wouldn't compress the struts together because the pressure would get into the lattice, but the actual struts themselves would get squeezed. And if there were any internal cracks there, this would fix that. And so another project with MIT Lincoln Labs is they have these inks that are tungsten and nickel, or a combination. And tungsten has a melting point of like 3600 C. So we're trying to do this overmolding idea that I just mentioned in polymers. We're trying to do it with ceramics now, where we can make 2 parts that have like some sort of complex mating surface, and we can put the MIT inks into them, and then we fire them. Basically the ceramics consolidate. The tungsten might melt to some degree, particularly if we alloy it more with nickel, and we could get conductive materials inside of dielectric materials. And you could do that to make an antenna or a strain gauge, but an interposed structure that could go up to 1,000 degrees C with no problem. And if you think about, there's a lot of applications like jet engines, gas turbines. There's just a lot of applications where having a sensor or an antenna would be pretty interesting. You're not going to put a microcontroller in this, because if you did, it would be vaporized at 2,500 C. But these inks and the dielectrics are enough to be able to give you some basic sensor type, functionality. And so this is an ongoing project. This is a tough one though, because melting tungsten's tough, and curing and printing ceramics is also tough. So this is sort of a very ambitious project. And then I can tell you, I did another project where I don't know if you've heard of Desktop Metal, but it's an MIT spinoff. They say they can print these metal objects with material extrusion, and they debind the plastic out, and they furnace it. And so I thought, well, I want to do an antenna, because they could do copper. I want to do an antenna that's just like crazy hard, and I called it a pathologically complex antenna. And if you hear about the word pathologically, okay, so usually that means like a pathological liar. So it's usually has to do with pathology, which is your health, and it's usually about mental health and being like a bad person. But in computer science, pathological means, or in math, it means like an intractable problem, like an algorithm that just can't be done. So that's kind of why we used it. It just sounds cool. Anyway, digital manufacturing of pathologically complex 3D printed antennas. That's just poetry. I mean, I love writing a good title. Anyway, that company couldn't do it. So we went off and did it a bunch of other ways, and went to NASA Glenn and tested the antennas, and they worked pretty well. And this one in the middle is funny. It's binder jetting. So we have a lot of these at UTEP. It's still stainless steel, I think, and it's infiltrated with bronze. And I had it done at this company X1. They shipped it to my house in this box, and my 16-year-old daughter ran over the box, which is right outside the garage. You can see the tire tracks on it. And you can see this thing did pretty well. I mean, it broke right here, and it's certainly deformed. there's two different pieces, but it survived. And it's a very fragile structure with all these overhanging kind of twists and turns, very serpentine. I thought that was, yeah, it was kind of just interesting, a testament to the strength of the materials in the latest generation of additive manufacturing. And this is an antenna, and we're actually starting a company over this. This is a ship in the bottle. This is a pyramid, and this is a pyramid, and it's a fractal. And what that means is this triangle has got, you know, 3 triangles in it, and that triangle has 3 triangles in it, and it's sort of self-replicating. I don't know. It's a geometry thing. And it's got this triangle inside of it that's a ground plane, and this is the irradiating element. And you can, right here, put a coaxial cable on that, and you can use this as an antenna. It's very broad band because it's a fractal, and it would fit in a UAV nose cone. We're about to potentially write a proposal to put it into little CubeSats, satellites that are pretty small. And so, yeah, anytime an engineer does a logo, it's just sad. But yeah, anyway, there's a company coming to pursue, you know, electromagnetics using additive manufacturing. And that could be the dielectrics, like I showed you with the zirconia, but it could also be aluminum in powder bed fusion. This was done with an EOS M290, which it turns out UTEP has. Okay, so I'm going to switch gears a little bit. This is sand, and now we're inkjetting down glue into the sand. And what we're doing is we're creating molds that you can pour metal, molten metal into. And this is what I've been doing a lot. YSU, Youngstown's a casting city. It's a metal town. It's sort of a rust belt place. It's sort of deteriorating. Every president since Reagan's tried to reinvigorate the city. It's like Detroit, kind of. So this is like our you know, attempt at doing that. So we 3D printed that green cube, and there's a hole on the top, and you could pour metal into it. You can make crazy structures you couldn't cast otherwise. So this lattice, for instance. Then the sand is disposable. You just bust that off, throw it away. Sand's cheap. It's like most of the Earth's crust is sand, silicon dioxide, and you can then make, you know, a casting you couldn't make otherwise. Okay, so that's pretty cool. And I could scan your head, and I could pour metal, and I could make a statue of your head, and I could do that in about 3 days, and I could probably do it for $400. And casting, of course, is like an ancient manufacturing technology. So what's cool about that is people trust it. They don't trust 3D printing, but they trust casting. But if you can 3D print the mold and then use a trusted process, you get the benefits of both worlds. I'm working with Ford, GE, Lockheed Martin, a lot of interest in this. But that's not what I do. I shove electronics in this stuff, right? And so this is a little Bluetooth sensor. It's got pressure, temperature, magnetic field, rotation, acceleration, and I'll put it into little cavities. So this is 3D printed, and that's a core. And what that means is it's something that would be suspended into a cavity, and that thing gets basically submerged with molten metal. And for about 2 minutes, these electronics live and report to Bluetooth to my tablet all of this data that nobody's ever seen before. It's just impossible to get this data without having some sort of wireless technology and a sensor in a very small package. And so we just published like mad on this. And yeah, it's just so cool. They last typically 120 seconds. So this is magnesium, and that's my cell phone right there. And there's a sensor deep inside of this 3D printed sand. I can tell you this is an aerospace part. I can tell you what it is. And I can tell you that magnesium is very dangerous. And I didn't know that because I'm an electrical engineer. But watch this. I'm going to go around and I'm going to get near this stuff, and I'm going to show you my phone. And you're going to see that we're collecting data from deep inside of this mold. Acceleration. So that tells me if something shifts, if something gets banged, rotation, humidity, pressure, magnetic field, just so much cool stuff that's unprecedented. Nobody's ever done this. And so, you know, you think about UTEP, it's a metallurgy school. I mean, it's you know, one of the 6 last metallurgy schools. So I'd really like to, you know, and do a lot of this Internet of Things and 3D printed sand molds, you know, moving forward. Here's a project with Penn State. Now this is simulations of 2 molds, a traditional mold. This is a casting, and this is a sprue, and this is the sprue and the gating system. And the color is the speed of the metal. And you don't want metal to go fast because there's turbulence, air entrapment, and it causes porosity. And you can see in the CT scan here that this doesn't do very well. Here, Guha Managaran basically does a helix, and he throttles back the velocity, and it fills up like half the speed, but it fills up slower and with much less porosity. And so what I did was put magnetic sensors down at the bottom of this runner inside the mold, and I could tell when the metal went by one point and the other point, timestamp them. I know the distance, I get the average velocity of the initial front. And so we wrote a paper with Penn State on that. And I just think this is cool, but this idea, that's molten metal that you're watching flowing, right? It's a simulation of it anyway. And there's just so much cool stuff you can do with 3D printed sand and molten metal. And molten metal is just so much fun. I mean, you saw my phone was cracked in the last one. Actually, that was because I dropped it the day before. I did have a student that dropped a phone into the molten metal, and it caused me a lot of grief because I used my Pro card, and I bought her another phone. And I guess, you know, buying student cell phones is, I mean, to me, it was data acquisition, right? It was a laboratory equipment. I'm just buying more of it, but I got in a lot of trouble for that. They took my card from me for like a month. It's terrible. So here's some 3D printed sand. This is an experiment I did like 2 weeks ago. And what's happening here is this thing fits down into a cavity also, and it fills up. And these, there's 4 of them, are cores that hang down from the ceiling. And as the metal fills in, this sand, which is 3D printed, it starts to decompose and it builds up pressure. And that's a real problem. And so we're measuring the pressure with these 2 sensors for redundancy. And we're hoping to actually cause, in some cases, bubbles to pop out into the metal and cause problems. And then in this one, there's no ventilation, but this hole right here is like a chimney that goes all the way down, and it lets the gases escape more easily. And that's an advantage of 3D printing. And so we did that, and sure enough, we see that the unvented cases, you know, case goes up higher. The really vented cases still has pressure, which was a little surprising, but not as much. And then there's 2 intermediate cases as well. And we're hoping to get a paper. We're in a revision now. This wasn't enough data for them. They wanted us to do more work. And then I submitted this right during the pandemic. It's just been a real pain. But I think this is a really, like, it'll be a seminal paper. And then this is really cool. So one of the things about 3D printing sand is you can do these lattices. The problem is if they're spatially varying like this, they're thick here and thin here. You pour the metal here and it comes down and fills in, and it'll prematurely freeze. These lattices have such high surface area that they freeze off early. This is like 2 inches shorter than it should be. So we have a project with this furnace company. We're going to put coils of around the core, so you can't see, but that lattice is in this core as a negative, and the metal comes down, over, and up, and we're going to put electromagnetic energy into it to keep it molten, and also the electromagnetic energy will push it up by something called the Lorentz force. And so here's an example of us doing a simulation of that. So this is another tragedy of the pandemic. It should have a paper already, but it's on hold for now. But I think it's just a really cool idea. And I love to print lattices. You can see that. But these metal lattices, you know, particularly like this, spatially varying, you know, I want to get one of these. They're like 8 inches tall, 4 inches in diameter. Take a sledgehammer, you know, and it's just going to immediately give because it's got tiny little struts. But the farther you go in, the thicker and stronger it is, and it'll slow you down. So you think about the applications of a car bumper or something like that. You could really minimize damage and absorb energy at unprecedented levels. So yeah, I got a lot of work going on in that. IoT. So it looks like we got another logo here for a company that actually I've had for like 15 years, but I'm resurrecting it. Do a lot of IoT. These are the sensors you just saw. TI has some really good ones. They're a little bit bigger. And then this is a Raspberry Pi. It's a Linux computer, and you can put a hat on it. So Alex Gomez, who's probably on the line, is designing one of these. And Callan Herberger, who's also probably on the line, is writing the software to basically get this data from the molds out. This is bigger, but we think we can get it down to like $5 or $15, so they're just disposable. You just throw them in the mold, pour metal, forget about it. And we've got this thing, because it's a Linux computer, can serve up a website, right? So you can actually write in the IP of this sensor inside the sand, and it will start reporting to you in HTML, you know, and show you the data that it's collecting. And so it's just really cool. And so there's definitely some commercialization opportunities here. And there's a lot of interest, you know, in just reinvigorating American manufacturing by juicing it with electronics, taking this 3,000-year-old barbaric, you know, casting process, which is so cool, and then just making it smart. And I think there's really nobody that's doing this kind of work. And there's a lot of people watching it. I was invited to be the keynote speaker at the American Foundry Society meeting in Cleveland, which unfortunately was virtual, but it was pretty interesting. Pretty close, I think, to the end of this. I'm sorry, I'm going fast. It's a water hose of data. Another thing I do is a lot of computational geometry, like trying to measure complexity. You know, if you're going to cast this, you have to have 3D printed sand. If you're going to cast this, you definitely don't want 3D printed sand. It's too expensive. So can you somehow look at an object like this, it's just an impeller and a gas turbine, and can you look at it geometrically and say, wow, that's complex, you better 3D print it, or say, no, please don't 3D print it, it would be a waste. And so I've been doing, and this is like a very poetic title, the economies of complexity in 3D printed sand molds for casting, as opposed to the economies of scale, which I'm trying to coin that phrase. I think it's kind of cool. But the idea is, can you mathematically determine how complex these are? And I've got another paper coming out with a couple famous metallurgists, which it's been kind of stuck. But okay, a couple more things. I think I got 2 more things to talk about, and I'm trying to go fast before you guys go to sleep. This is an EOS M290. You've got one at UTEP. That's the one at Youngstown. I do high-speed imaging, just like your eyes. If you have 2 cameras, you can do binocular views, and you can judge depth, and you can do a 3D image basically. And so that laser is coming down, lasing the metal powder, and stuff shoots off called spatter, and it's not good. But if I can see that spatter, identify it where it starts and stops in a 500 microsecond exposure, like in this example, it stopped. You see 2 spatters right there. There's a third one that's not identified. I can tell you where it starts, where it ends in 3-dimensional space. I can then tell you how fast it's going, where it's going, and how old it is. And so we were doing a bunch of studies on spatter tracking, because spatter oxidizes, and if it falls back down onto your design, it can introduce a defect. So understanding spatter is just something that they don't really know yet. And there's a lot of research in it, but I think I'm the only one that's actually used Stereovision to track it in like high-speed imaging. And then here's another one. I'm about to buy this in my UTEP startup package. This is a Keyence laser line profilometer. So that's a laser line right there. And this is attached to a recoating blade that would come across and put new powder on the powder bed. And while it does, that purple line can go across and it can do this really high resolution surface map. And then based on some work that Medina and Wicker did that I wasn't a part of, but sort of inspired me, I did a design where I put in intentional holes that are like intentional defects, and that I could actually identify those defects by using this Keyence scanner. I'm getting this scanner next week, or maybe the week after that. And there is a university in Switzerland, ETH Zurich, that wants to reproduce my results with this equipment with a polymer powder bed fusion system. And this school is cool because it's Albert Einstein's like alma mater. So, and of course, Switzerland's just cool. If you don't know, it's a really cool place to go visit. Mountains, Alps, it's beautiful. So give me an excuse to go there, because I think this could really be commercialized to improve the quality and the yield of different powder bed fusion systems. And then this is powder bed fusion. So there's the laser. Here, this is just something I did on a weekend, but computer vision, where it's scraping powder across and adding more and more powder, and the laser melts it. But these lines are bad. And so I've used computer vision to just sort of find the lines. And like right now, I get this number, it's low, right? It's 0. So now it's really good. But look, now it's 55. So you got a problem maybe. Now it didn't go over the build, so it doesn't matter, but just sort of an interesting application of computer vision to improve additive manufacturing. And then I'm pretty sure this, no, maybe this isn't the last thing, but this is really cool. That's laser cladding. And it's basically blowing metal powder in a laser, and it just sort of draws an object in metal. And we made tensile bars in green, but we first made these little inserts and we shipped them to the University of Bremen in northern Germany. And they screen printed on ceramic sensors with 4 layers. And then they shipped them back. We put them into this cavity, and then we basically laser clad over it. We could measure the temperature while it was being made from within the object. And then we pulled the tensile bars and we could measure the strain. And so here's the sensor that the Germans did for us, which is kind of cool. It's that red thing. And we're about to do another one. And these are the 2 contact points you use to read it. And this video kind of shows the evolution of that insert. I think this is a technology we don't have at UTEP. It's directed energy deposition based on laser cladding, but I'm definitely going to be working on that. So there's the insert from Germany stuffed into that tensile bar. Now watch this number here, which is resistance. I'm going to stitch weld these in. All we're doing is popping it with the laser to melt it. So they become one piece. And look, you see it climbing. It measures that. But then we're going to put metal on top of it. So you're going to see spatter shooting off. You see, I don't know if you guys can see that, but it's adding metal line by line. And this thing is reacting to it. And then this is the cladding. It looks terrible, but we can machine that. And you get these nice smooth surfaces. Only 2 of the 10 survived, by the way, because we just melted the hell out of it with the laser. But we did basically, and there's the 2 connection points. So you have a sensor in a place a sensor shouldn't be, right? Where you normally wouldn't be able to access the location. And so while we built it, we got data. While after we built it, we got end use data, and that's pretty cool. And then my friends in South Africa looked at the bad ones, and you can see that's that little conductor, and it popped off because the laser cladding just heated it up too much, and it was destroyed. And then this is cool. This is actually Frank Medina before he was at UTEP, or as a professor anyway. This is another type of laser cladding. And what I want to do here is, the cool thing about directed energy deposition is I have an unobstructed view of the object. This is just a Lulzbot printer. And I took that STL and I used computational geometry to say, from this location and at layer 5, 6, 7, what should I see? And then I colorized it just based on the Z height, just to make it look cool, because it should be hotter on the top. But I can compare these 2 things, the geometry and the actual image per layer. And I could say, yeah, you got deformation or you're going bad. Now, you would never do that necessarily for this cheap $1,000 printer. And that's Medina. And this is a RPM system. And this is just a monster direct. This is one of the best 3D printers on earth. You fill this whole chamber with argon, and it's just got a laser, and oh, it's so cool. Anyway, Frank got this, and then he came to UTEP afterwards. And I worked on it after he left the Edison Welding Institute in Buffalo, working with GE Global Research in Albany. Speaking of which, a lot of thermography. So this is an image of just a melt pool that directed energy deposition. This is a CMT welder on a 6-axis robot, and it's about to start building that cylinder. You see that's bright. So I'm going to do thermographic stereovision, where I can actually get 2 cameras. That's one. I'd get another one here, and I could actually watch in 2 different perspectives the temperature up to 2,000 degrees Celsius. But because I could do stereo vision with 2 cameras, I can tell you where the melt pool is in 3D space over a time period. And there's a company in Colorado, Big Metal Additive, that does wire aluminum DED with machining. They just did these marine landing pods that they tested at Camp Pendleton in Southern California, and it really went well. And I'm trying to get into their shop. They're near the Colorado School of Mines near Denver, and put these cameras in there and just collect a lot of data where I could just see where their welder is in time and in XYZ space and in temperature, and then just recreate like data that I don't think anybody else has ever done. I've never heard of anybody doing thermographic stereovision. So I'm really concerned, because I've mentioned it at least 10 times in the last 10 months, that I'm about to get scooped. So I'm accelerating this. My foot is on the accelerator for sure. And it's a cool application of computer vision. So this right here, these arrows we superimpose, right? That's the thermal gradients. And my friends at GE, that's what they're really interested in. It isn't so much the temperature, but the change in the temperature and the direction of the change in temperature and how that affects the metallurgy, which of course I don't know anything about, but I enjoy working with people that do. And then I guess I'm done. I hope that wasn't too long. Oh, 45 minutes, perfect. So of course, this is one of the things I love about UTEP's Bhutanese architecture. When I was 6 years old, I lived in El Paso, and my sister went to college here. She was babysitting me. So this is the first college I ever attended. Calculus class, had no idea what was going on, but I immediately recognized the cool architecture. And then I just noticed that this is actually a Bhutanese picture. And so I thought it was sort of cool. I always throw this up when I'm out in another country giving a talk. So I basically say, you got an open invitation to come and visit us, but I can't say that to you guys because you're already here. But of course, you're always welcome to come and talk research with me. So with that said, Myra, I guess I'm done. Is there any questions?
Awesome, thank you. And actually that Bhutanese picture you have on the bottom left was the exact picture they used for inspiration to build the UTEP architecture. Yeah. So
that's funny.
That's when you go to orientation or like do something around UTEP, that's the same picture they always reference. So cool. I was wondering, do you have time to maybe open it up to some questions that students may have? Yeah, so if anyone here has a question, just use a little toggle to raise your hand, or type it in the chat so that Dr. MacDonald can answer that for you. Okay, Dr. Khan, go ahead, Dr. Khan.
You're going to talk to us, right, Dr. Khan? We can't hear you.
I think you're muted, Dr. Khan. So remove the mute and you can go ahead and ask your question.
He's probably asking some brilliant question right now.
I know, and we just can't hear.
It could be a hard question. So maybe it's good. No, so you can't unmute. Okay.
Yeah, Dr. Khan, I think you just need to unmute yourself. At the top, there should be a microphone. Just click that.
Still
this
no.
is the bane of
I got it.
Oh, there you go. Yes, yes.
Thank you very much. Okay, this is very exciting, Eric. I'm very excited, and the work you have done. Actually, I don't know how you can manage that many of projects together. You are really awesome. You are really
high blood pressure.
Yeah, I know many of your works, but from today's presentation, I got the really latest information on what you are working. Okay, this is cool and exciting. So you are working on many 3D printed system and IoT and electronic sensor, etc., etc. Okay.
You're talking about the sand casting.
And my question is related to the application of this item for the space or satellite, or maybe a kind of satellite related electronics sensors for our future, so that we can survive if there is any Star Wars or something like that.
Well, yeah, okay. So this peak, it turns out, is space qualified. That's one of the reasons why I picked this. So this is got satellite written all over it. The problem is it's hard to print because it has a high temperature. But yeah, back in 2013 at UTEP, working with the University of New Mexico, we had a small piece that was put into a CubeSat and flown into space. And a facsimile of that was actually put in the London Museum of Science, the oldest science museum on Earth, and was shown as an exhibit, which is kind of cool. It was right next to that gun that UT Austin student had printed. It got confiscated. But in any case, satellite is definitely any kind of space, aerospace applications. If you got something for me, let's go for sure. I know that Joel Quintana and I have been talking for sure. And he has a launch next year, right?
Right. And the reason I'm talking this issue because I'm from Japan, right? I have been there for almost 16 years over there, and I worked on many satellites. I developed many electronics and sensors, but I have a very strong desire to work on that, and so that we can apply this technology for the space applications.
I love it.
I have a huge knowledge on the space environment, how electronics works there, and my dream idea is, in space there is a lot of plasma, right? So my objective, actually, that is my dream, so that I can use this plasma to accumulate the charge in 3D printing system, maybe capacitive or inductive, whatever it is. And then we can use this energy to charge our battery when we are going for the deep exploration, where sun is not the source.
Right. So it's like energy harvesting of plasma in space. Oh, that sounds
right.
Great,
using the
great
plasma,
title of the paper.
Using the plasma, and we can develop some kind of sensors or some kind of storage system. It might be capacitive, it might be inductive, or it might be some other mechanism using the 3D printed system. This is one. And the second one, I'm thinking actually to make some kind of onboard repairment tools, so that we can develop, we can sense it, where the location of deformation or where the location is for the damage, we can repair something like that. Okay.
Yeah, right.
Actually, yeah, I have many ideas on that, and I really want your time so that we can talk face to face, and we can share our knowledge.
I So anything that has to do with space, I get real excited about. I don't really know much about it. I was a chip designer in the 90s, and I did work on radiation hardened microelectronics.
Right.
So I know, I understand like rad hard stuff where the radiation of space can cause little bits to flip, soft errors. And gosh, we had another project where we did plastic with tungsten powder embedded to shield X-rays and radiation. And we proved at Sandia National Labs that we could do that. I think there's so many applications. And I can tell you that, yeah, I picked PEAK. One of the reasons why I was so excited about this material is because it's one of the 3 thermoplastics that's allowed to be used in. So Ultem, PEAK, and PEC are the 3 that are currently space qualified by NASA. Like if I show them like a polycarbonate, and I got all these electronics in it, they're just like, we don't care. That's boring. I show them this and they start, shaking. So, and it looks like it's really weak and not very strong, but this stuff is like, it's just amazing.
No, we have a huge actually area of where we can explore this type of conditions, or we can design something, we can propose something, we can start some, we can design some prototype to test it. I have a huge knowledge on testing of space materials. I can share my knowledge with you, and if you allow me to meet face to face, probably we can talk more detail on that.
Definitely. All right, you're on, man. We'll publish like mad. It'll be
right. There is a huge area on that field actually. We can work.
And if we could get money, if we could get funding,
definitely, no doubt. Yeah, no doubt.
Get some massive funding.
No doubt.
Pay for some of these students. Yeah, definitely. Correct. I'm totally on board, man. Let's go.
I'm sending an email request so that we can make a common time, and please give me 30 minutes to 1 hour so that we can talk on that issue and we can design something together.
On it. We'll do it.
Thank you very much. Thank you. I'm really, really very excited on that. Thank you very much, Dr. Eric.
Definitely.
Anybody
else? Okay, thank you, Dr. Khan.
Thank you. We did get some questions in the chat about, working for the KEC and needing a social security number for students who are Mexican citizens or not U.S. citizens. And I will say that if you do get a position at UTEP, you can go to the OIP office and they will help you get your paperwork done. So that shouldn't be an issue as long as you have your offer letter. I will also say that the KEC Center recently sent out a flyer. They are looking for undergraduate students who are and are not U.S. citizens. So some of their projects you will need to be a U.S. citizen, but not for all of them. So don't let that be a deciding factor for you. And I typed in the chat the emails where you're supposed to send your resumes. I did see that they got a good amount, so I think they're still sifting through them. So maybe just give them a little more time to, reach out to you to see if you were one of the students selected for a position. And we did get another question, Dr. MacDonald, if there are any requirements or possibilities to work with you specifically in your research.
Gosh, not really. No, I mean, just like a lot of passion, right? You can see that I'm kind of hardwired with a lot of energy. And so I tend to be very aggressive about pursuing things. I worry that people are about to steal my ideas. And so I'm constantly just go, go, go. And it's probably unhealthy. I probably work a little too hard, but I like to be hyper productive. So that's the main thing, is if somebody's really passionate about this and wants to do something remarkable, then that's what I would recommend. And some of my best research students were certainly from Mexico. And as a matter of fact, I was just saying to my class that I'm intending to do, my wife and I are expecting to go down into Chihuahua, and we want to do the Copper Canyon, go to Creel, go to Cuauhtemoc. I like the Mennonitas. There's a lot of German Mennonites down in Cuauhtemoc, and their cheese is really good. So I'm a sort of a Mexico-phile, I guess, a lover of Mexican culture, always. And other foreign students as well. Some of the stuff we're doing for sure is sensitive in terms of, it requires U.S. citizenship, but plenty of it doesn't. And we try to keep those projects open to, students that wouldn't be able to take the other projects. I know that the president of the university and I are going to Sandia National Labs on October 8th, trying to reinvigorate that relationship. So it's the Department of Energy. It's a famous national lab that invented the atomic bomb back in World War II. And it turns out that there's like security clearances that I don't have. So like, I'm going to go to the first part of the meeting, and then the president's going to kick me out. And I'm going to go talk to other researchers around the lab while they talk, her and the director of Sandia. So yeah, we definitely will. We can take anybody and research it. It may be longer, it may take more time, depends on the funding source, but certainly we're interested in having a very diverse group of people thinking about things differently from different perspectives, for sure. So
one student was asking, even if they're a freshman, do you think they should still take a chance and apply?
Oh yeah, no, actually, I like to get students from high school if I can, because a lot of what we're doing isn't like you don't need to understand differential equations. A lot of it's pretty intuitive. And if a student can come in and start to run a system and learn how to print and get that history, then we'll have them for 5 years or 4 years as opposed to just their senior year. So no, the earlier, the better. And then if you decide to get a master's degree or a PhD, then we just take it to the next level. And you know, at that point, we can do something crazy and spin off a company or write 10 papers that makes us famous, if not rich. I'm poor, right, but cool, right? someday. Yeah. I'm joking, kind of.
You don't want to stay living with the grad students forever, right?
That's right.
So to work with you, Dr. MacDonald, do they just apply with a Keck Center, or do they apply directly with you? Where is that funding source coming from?
Well, I would say go to the Keck Center first, because they're hiring a lot more people than I am. I just got here. I had 2 positions. So I hired I brought a student from Ohio with me, and Alex Gomez is somebody I knew from UTEP when I was here before, and he was at Sandia, as a matter of fact. So I pulled him in. So it may take me 4 or 5 months to get funding as I write proposals to the federal government. And so I know the Keck Center is just, they're doing all kinds of things. And the other thing would be just, to talk to me, to be aggressive, because I work really long hours. And I get approached by a lot of students, but the ones that are tenacious are the ones that are more likely to get the position. And generally, if there's even maybe a small project that I have that you could go work on where there's no funding, but you could design some little part of the project I'm working on, then I could see the quality of work and see the level of commitment of the student, basically. And that might help also. Generally, I don't like to hire students that I don't pay, though. It seems like it doesn't work out that well, but it is an opportunity for a student to show a level of interest and passion for the research.
Right, definitely. If there are any other students who have more questions, please feel free to raise your hand or type in the chat. We are at the 1 hour mark, so we want to respect Dr. MacDonald's time. So if there aren't any more questions, we will close out the meeting, but we'll hang around a little bit in case someone has a final question.
Hey, so one thing I see is there's a French PhD student, Alexis Morel, who's online with his soon-to-be wife, Anna, and he's a Fulbrighter. He just got a grant to come to the United States to work at UTEP. And he's going to be working on 3D printed batteries. I didn't even mention that because that's a whole nother cool area. But he's from one of the best research groups in the world for 3D printed batteries. And I talked him into coming to UTEP, and he's going to love it. Hello. Hey, how's it going? So you guys are in France right now, right?
We already had dinner right now.
It's 9 p.m.
Well, I hope I entertained you to some degree. So in any case, there's so much stuff. What you saw was just me, the scratching of the surface. 3D printed electronics, you throw batteries into that, it's just so exciting, because then you can print the whole thing. My dream is to be able to print a robot and have it walk out of the printer. And I can't do that without a battery being included and, some energy source. So we'll be one more step closer to that next year. But the other thing is he has a Fulbright Scholar Award, which is a very prestigious U.S. State Department grant. It either brings students or professors here, or it sends students or professors elsewhere. And so I spent a summer in South America, Chile, doing research at a university on the South Pacific. And so if you guys aren't aware of that, you need to be. It's sort of inspired by the Rhodes Scholarship that they do in England. Fulbright was a senator that was also a Rhodes Scholar. And so he wanted an American version of that.
Okay, Dr. MacDonald, I did type in your email in the chat. I hope that's okay, so students can reach
Sure.
you. They did ask about your office hours, and I know since campus is kind of empty right now, yeah. And your office is still TBD. I did type in email, so students, please feel free to email Dr. MacDonald. You know, these are great opportunities that he's presented to us. Oh, hey, Dr. Flores, Dr. Flores, you just joined as we were about to end this. But as I said in the beginning, don't worry, we are recording. We did record this session. It will be uploaded to our YouTube channel either today or tomorrow. Thank you so much, Dr. MacDonald, for your time. It was all fascinating. I have no idea when you sleep, but I hope you do get some sleep.
Well, I'll say this. I'm pumped to be back, and I've eaten menudo every single day since I returned.
Wow.
Don Cucos. It's so amazing.
Yes.
So anyway, well, I appreciate you guys listening for sure.
Thank you very much. Thank you.
Definitely. Talk to you guys.
Awesome.